Hi everyone. Today I'll be talking about a family of coupled KdV systems. This work that I have done in ICTS with Manas and Vishal. Before we go to the coupled KdV system, we'll look at the classical KdV equation. This is a prototypical nonlinear wave equation, and this has been seen to be the relevant framework for a wide range of physical phenomena, ranging from geophysical flows, nonlinear optics, and more recently in Bose-Einstein condensates. Another notable feature about this system is that it is integrable and it has an infinite number of conservation laws. Furthermore, it also supports soliton solutions, which basically which entail a balance of nonlinear effects and dispersion. The picture down here, you see one such form where the form of the soliton solution actually remains constant as it propagates to the right. You can think of this as the time axis and this as the space axis. Now, this is the coupled KdV system that I'll talk about today. For the large part, you can see on the left-hand side, it's pretty much the same as the classical KdV equation. On the right-hand side, we have all forms of coupling. The coupling is parameterized by a set of real constants WQ, and there are m of them. This m can be any integer which is greater than 1. So I will talk about some properties of this particular system and how we end up with the system and some of the solutions pertaining to this kind of a system. So first up, I'm trying to get the important results out of the way. So this set of coupled KdV equations can be derived in, basically has got an Hamiltonian structure and can be derived variationally. For the time being, in the next couple of slides, we'll see what the precise forms of omega and theta are. But for the large part, I do not want people to focus on what exactly these forms are. The calculations are long and tedious, but just understand that this is a system which has got a Hamiltonian structure regardless of what the number of field variables that we have in the system. Now, what exactly is a conservation law? As I said, like in the classical KdV equation has got infinite number of conservation laws. If we have a quantity, whatever script T and script F, and they obey some law like they're governed by this partial differential equation or by this integral differential equation, you have a conservation law. The present system, we have only 3 conserved quantities, unlike the classical KdV equation. And the first one is the trivial one. This is just given by the set of equations themselves because they are already in this particular form. The 2 non-trivial ones are what I'm calling momentum. And when you integrate this T2 over space, that's when you get this the momentum for this configuration, and that goes back into the definition of definition for the Hamiltonian structure. Likewise, we can also define the Hamiltonian, and again, I do not want you guys to focus on the expressions given here, but the fact that this quantity exists. Again, upon integrating in space, we get the expression for the Hamiltonian theta. And so at this point, I think we can pause and reflect that we have a set of coupled KdV equations. And this is true for every integer m greater than 1. And all of them have a Hamiltonian structure. This in itself is not a very trivial statement. And the other important thing is since we have only 3 conserved quantities, the main thing is that this is not an integrable system. Again, this is not a trivial system where a non-integrable system has such a clean Hamiltonian structure. Okay, now where does this coupled system come from? So it's not something that we cooked up. The details were published in an earlier work in the group. So our starting point is a multi-component nonlinear Schrodinger equation. It's got both self-coupling and cross-coupling terms. We can move to a hydrodynamic description using something known as the Madelung transform. So where the wave function is so where we move from the wave function to a set of variables, density rho k and velocity vk. Then what is done is like a perturbation analysis about a base state. And with this kind of an approach, we can do a complete characterization of the linear problem. We can obtain all the eigenvalues and the corresponding eigenvectors, which is kind of important because we can then express these perturbations in terms of those field variables UP, which were the final variables which appear in the coupled KdV system. The KdV system itself emerges when we enforce the solvability condition for higher order corrections. There is always a system of KdV equations. Whether they are coupled or not actually depends on the fact if this particular criteria is satisfied. This was proved in another paper earlier which was published from the group earlier. And those parameters which I said, which characterize the coupled KdV equations can be derived in terms of the base state densities of the original system. So Wj is something like this. One more important point is if we need a system of M, if we have to get a system of M coupled KdV equations, the number of components in the Schrodinger equation should be at least M plus 1. Again, I'm not going into the details of this, but I can discuss it with anyone who's interested later on. Now, so far I've spoken about some conservation laws, that it's actually a physically relevant system that emerges out of the nonlinear Schrodinger equation, and it's not something cooked up. Now we'll actually we'll try to discuss some solutions. So we take the simplest possible KdV coupled KdV system, which is basically M equal to 2. The set of equations is here. We make one ansatz. The two fields U1 and U2 are both proportional to another function phi. This set of these two KdV equations will reduce to a single KdV equation if this particular condition is satisfied. And upon solving this, we get like three possibilities for this ratio. This is effectively an amplitude ratio. So under these conditions, basically we have a single KdV equation, and again we can use all the classical tricks for getting solutions for the KdV equation. And this is something we use something known as the direct method. By defining an auxiliary function, you can define multiple soliton solutions. So in this particular slide, I'm just showing you expressions for a couple of them, the one soliton and the two soliton. When I'm talking about a one soliton, that means that like the solitary waves has got a single peak, and a two soliton likewise has got two peaks. Okay, now this is as far as we can get analytically. Now we have to turn to numerics. First up, like we need to, I'm going to fix the nonlinear Schrodinger equation. We are going to work with 3 components because M was equal to 2 in the previous one in our system. And I also give you the linearized hydrodynamic equations. This is to kind of highlight the fact that nonlinearity is essential to capture the observations that we do see. So first up, I will show something with a 2 soliton. So what you see as analytical is the prediction given by the KdV system, and numerical is a numerical solution of the nonlinear Schrodinger equation. So initially, the two peaks are apart. They approach each other. This is a feature of soliton solutions. So the predictions are very good in the process of approaching. During the merger, there are some deviations from the theory, and post the collision, when they start to separate out again, the original form is maintained, but the location is slightly off. If I were to have, if I had shown instead the solution for, if I had shown instead the comparison for the one soliton, the match would be even better. But I thought this would be a better illustration of the fact that the limitations and the benefits of our approach. So the second thing is like about, do we actually need non-linearity? Here, there are two simulations here. The numerical is again the simulation of the Schrodinger equation. Linear depicts the solutions obtained by the numerical solution of the linearized hydrodynamic equations. And pretty early on itself, you can see that the linear solution kind of starts suffering from radiative loss. So the form is lost and it's no longer, so basically what you can take away from this slide is the fact that it is, nonlinearity is an essential feature of this theory. And the last thing I'll talk about is like, could we have started with any ad hoc simulations and just ended up with soliton conditions for the Schrodinger equation? That's actually kind of true in the KdV system, where you start off with a general perturbation and it kind of decomposes into various soliton solutions. But that's not the case here. So in this case, I just look at the, I fix the density to be the same. The only thing that I change is the velocity, or in this case, the phase of the wave function. And pretty soon we can see again, there is a departure from the original form. So to conclude, basically we have found a new non-integrable system of coupled KdV equations for every integer greater than m. It's not, most of the work in the literature pertains more to where they fix the number of equations and they cook up equations like this. But like in our case, we organically got something from a relevant physical setting. So regardless of the number of systems there, as I said, like we always get, we always have conservation laws for mass, momentum, and Hamiltonian. As I said earlier, that this system has got a Hamiltonian structure, and the fact that these equations are coupled, it happens only when the underlying system has got repeated sound speeds or repeated eigenvalues of the linear problem. And finally, the soliton solutions are seen to be robust in both the soliton solutions that we get from the KdV prediction is seen to be fairly well observed even in the nonlinear Schrodinger framework as well. Okay, thank you.
Thank you, Sharath, for the wonderful talk. Now we will take questions from the audience. Any questions? Yes, Logan, please.
Yeah, Logan.
So I had a couple of questions. So one is just a clarification. So when you say you looked at the linearized, like analysis, which had this radiative oscillations and so on, are you considering the linearization of the KdV, or are you considering the linearization of the nonlinear Schrodinger equation?
So this is the hydrodynamic, linearized version of the hydrodynamic expression for the Schrodinger, not the KdV. The KdV is purely analytical. Yes.
Okay. So the thing that you're plotting is,
yes,
this linearized hydro.
Is this, yes.
Okay. Okay. So second question, when you so you don't expect this coupled KdV things to be to be integrable. So you expect them to be not integrable. Yes. But could you do you have a numerical evidence for that fact? Like, for example, one check would be if you have multiple particle scatterings.
Yes.
You can kind of compare it against 2-to-2 scatterings.
That's
and of the solitons, but and show that you can't, the multiple particle scatterings are not determined by 2 particle scatterings. Is there some way to show that it is indeed not integrable by some such method?
Yeah, I think like we concluded that this particular system is not integrable because we weren't able to find beyond 3 conservation laws. So there are a number of ways in which one could define an integrable system, like an infinite number of conservation laws for basically an infinite dimensional system like this, or the existence of a recurrence operator, or basically if you can apply the inverse scattering transform, something similar to what you just said. So we have concluded this fact more on the fact that more because of the fact that we haven't found what to say, any more conserved quantities beyond the 3 that I've mentioned here.
Yeah, I understand the analytical argument. I was asking whether there's a numerical evidence.
Numerically, we haven't explored anything as such, and we haven't thought of any such approaches either. Maybe that's something we can talk about.
Yeah, I agree that it's probably not integrable, but it would be good to show that numerically. Yeah. Okay. Thanks.
I have a question. Hello.
Yes.
Yeah. So for the two component case, you said that for particular choices of this ratio, you can map this full problem to a single KdV phi.
Yes.
Right?
Yes.
So this KdV is this in terms of phi, it's integrable or not?
So this you're right. Like a single KdV is definitely integrable, but this depends strongly on this ansatz. So it's more like we found a regime or a set of parameters for which we can mimic maybe an integrable system, rather than we cannot claim that this is an integrable system, because this is not a universal aspect for all sets of parameters.
But this mapping after this equation of RQ and whatever, if it satisfies for these choices of R1, R2 and this phi, is an exact mapping, right?
That's right. And that is kind of the reason we can see soliton-like behaviors in the simulations as well. So
no, I'm saying, is it exact or it's approximate? That's why it is not matching after the collision, after the scattering. What is the reason that why is it not matching at later time?
Yeah, you're right. This is probably because it's an approximate theory. Because this was the original couple system was derived from a perturbative theory, that's probably why we have some deviations from the simulations and the analytical predictions. Is that
okay?
Yeah.
Okay. Thank you.
No.
Thank you, Sharath, again.
Yeah.